About 250 years ago, in 1752, a library of papyrus scrolls was discovered buried in the ancient Roman city of Herculaneum. And those scrolls had been charred and buried when Mount Vesuvius erupted back in AD 79. And although they were discovered and excavated 250 years ago, most of them still haven't been read. And that's because they can't be unrolled. They're too fragile. They break into tiny pieces. And today I'm going to talk about how we can virtually unroll them and read the text inside. That process starts from a micro CT scan of the scroll, which is a technique originally developed at the University of Kentucky. And CT lets us see fine cross-sections of the rolled scrolls, like this. But to actually read the text, we need to flatten it out. We need to virtually unroll it. In other words, we need to find where the original papyrus surface passes in the 3D scan volume to extract a 2D mesh corresponding to it. And to do that, we can train a neural network to predict where the papyrus surface is. And people have tried this in the past. But the predictions are never perfect. You get breaks in the predicted surfaces and sometimes false joins between surfaces. And that means it's hard to read off a nice surface mesh from the predictions. And there are various existing methods that try to do that by growing a surface progressively outwards, but they don't work with this particular data, which is too dense and too noisy. And we take a very different approach. Take a top-down, model-based view, because we know that originally the scroll was once one nice rolled-up rectangular sheet that then got distorted during and after the eruption. We try to invert this. In other words, we try to find a representation or a model of the original rolled sheet plus a deformation that distorts that into the shape that we now see in the scans. Now, idealized scroll model is just an Archimedean spiral, which is then extruded along its perpendicular axis. And if we think of it as being infinitely large, that only has one free parameter, the tightness of the windings, which in the equation is what we call omega. Theta and z are then curvilinear coordinates on the rolled up sheet, and the sheet is the locus of this S for all positive theta and z. And to map this idealized scroll to the distorted shape that we see in the scan, we use a diffeomorphic transformation. And that has three terms. The first is a coarse scaling term. The second is the integral of a stationary velocity or flow field, where we imagine each point of the spiral moving through a smooth flow, a bit like in medical image registration. And lastly, we have a local scaling of the gap between the windings everywhere on the sheet. And each of these stages is smooth and invertible, so the overall transform is as well. And if we can find it, we can move points between the idealized scroll and the real scan. So we optimize parameters of the deformation and the winding rate of the scroll, omega, all together just using Adam in PyTorch. We try to make them match the CT data, or rather to match some features extracted from the CT using existing pre-trained neural networks. Those networks predict which voxels are likely to be on the surface, which are likely to be papyrus fibers, and what the local normal directions are. So we use existing pre-trained public models for that, and then once we've got those features, we set up losses that encourage our deformed spiral to match these different cues, encourage it to match the noisy surface predictions and normals. The results that we get look like this. So in the top row, they show the perfect Euclidean Archimedean spiral before we fitted it, just overlaid on the CT. And at the bottom is the result after our optimization, where the spiral has been distorted so it conforms to the scroll windings. By pushing the CT scan backwards through diffeomorphism, then we can reverse the deformation and get back nearly circular windings from the deformed scan. On another scroll, P Herc Paris 4, here we see the inner 20 or so wraps, and we interpolate between the idealized spiral and the final version. In 3D on the right, you can see the outermost wrap distorting to match the scroll. And last, once we've fitted the spiral, it's straightforward to create a flattened volume out of it. We just sample out voxels that lie under the spiral surface. So in the first scroll on the top, that immediately lets us see some of the ink as bright regions, so we can identify some Greek letters. From the other scroll on the bottom, we use an existing AI method to make the ink more visible. And again, we can see rows and columns of text. That's all. At the top, there's a link to our code. And at the bottom, if you find virtual unwrapping cool and want to try, the Vesuvius Challenge runs competitions and has public datasets available. Thank you.